Welcome to the video lecture series of solid state devices. Course code EC301, contact hours 3 per week, credits 3, this is lecture 50. Myself, Dr. Shunipa Roy, Assistant Professor of Electronics and Communication Engineering Department, Guru Nanak Institute of Technology. This is Module 3, Device Physics of Bipolar Junction Transistor. Module 3 depicts the physical mechanism, carrier distribution, common base current alpha, beta, Ebermühl models, the lesson plan is formation of PNP, NPN transistor, energy band diagram, current conduction mechanism of CE/CP/CC configuration. So the objective of this lecture particularly is students will be able to know the formation of PNP and NPN transistors, energy band diagram, current conduction mechanism, CE/CP/CC configuration. So let us start with the history of BJT or bipolar junction transistor. The first transistor was a point contact transistor, and the first point contact transistor was invented by John Burden, Walter Brattain, and William Shockley at Bell Laboratories at New Jersey in 1947. This is one of the original pick of these three scientists, and this is the picture of original first developed point contact transistor kept at Bell Laboratory. So these are the few examples of transistors. Different type of packaging have been done here. So bipolar junction transistor is a semiconductor device conducted with 3 doped regions. These regions essentially from 2 back-to-back PN junction at the same block of semiconductor material. So the most common use of BJT is in linear amplifier circuit. As we know that it is used as an amplifier device. The 3 regions are called emitter, base, and collector. This is an NPN transistor. Emitter region is N-type, collector region is also N-type, but the base region is P-type. Emitter terminal is denoted by capital E, collector terminal denoted by capital C, and base terminal denoted by capital B. Base region is sandwiched between 2 emitter and collector regions. So base region is of opposite polarity of emitter and collector region, and the width of the base nearly of the order of 1 micrometer. And the collector region is most spacious region. Emitter region is medium, and this emitter region is highly doped. This collector region is moderately doped, and the base region is very poorly doped. So why emitter region is highly doped? Because it has to emit maximum number of majority charge carriers. As this is N-type, here the majority charge carriers are electrons. That's why this region is heavily doped or highly doped. Collector region, just the function of the collector is to collect these majority charge carriers emitted by the emitter. That's why collector regions are moderately doped, and the base region is poorly doped. So we define current direction such that the current IC and base current IB flow into the device, whereas the emitter current IE flows out of the device. From Kirchhoff's voltage law, we can write that IC plus IB equals to IE. Here, if this is the node and if we applied KCL at this node, then we can write IC plus IB equals to IE. That is written over here. So this is already mentioned that heavily doped, lightly doped and moderately doped. The base region is very thin. So what is BE and CB junction? BE is nothing but base emitter junction and CB is nothing but collector base junction. The PN junction joining the base and emitter region is called base emitter junction, and the PN junction joining the base and collector region is called collector base junction. BJT operation, let us start. How BJT works. The electrons collected by the collector at the collector base junction essentially form the collector current in the external circuit. There will also be a small contribution of collector current called ICO from the reverse saturation current across the collector base junction. The base current supplies positively charged to neutralize the electrons combining in the base. This prevents the buildup of charge which would hinder the current flow. So this is the schematic. This is NPN transistor. This is PNP transistor. This is emitter base junction. This junction is emitter base junction. This is emitter. This is base. Emitter base junction is forward biased as the negative terminal of the battery is connected to the N region. Positive terminal of the battery is connected to the P region. Similarly, here positive terminal of the battery is connected to the N region and negative terminal of the battery is connected to P region. So this region, collector base junction, is reverse biased and emitter base junction is forward biased. So this of the order of 1 micrometer and this of the order of 1 millimeter, total dimension of the device. This is showing the configuration of PNP transistor and this is showing the symbol. The outward arrow indicates it is NPN at the emitter, inward arrow indicates it is PNP at the emitter terminal. So this is the two-dimensional view that this is the normal substrate, either N-type or P-type substrate maybe. Then collector region is diffused. After that, base region is diffused. Then lastly, emitter region is diffused. So, if we cut the transistor across the vertical plane, then we will see this type of structure. The base region is narrow. Here it is showing that this is larger than emitter region, not that. Actually, if you see the cross-sectional view, then you will find the actual effect. The base region is very thin. Here the diagram is not at per scale, but base region is very thin. Collector region is mostly spacious, then emitter region. And the upper layers are contacts, metallization contact. And this hazy region is oxide layer to isolate these regions as well as the metallized contacts. So BJT constructed with 3-layer semiconductor device consisting either 2N, 1P layer or 2P or 1N layer of material. BJT is constructed with 3 doped semiconductor regions separated by 2 PN junctions. 3 regions are called emitter, base and collector. So now the concept of BJT basic transistor operation. Here we can see that emitter base junction is forward biased and collector base region is open. Here we can see emitter base junction is open and the collector base junction is reverse biased. Actually, this is not the case, but to make you understand, I have separated the 2 one figure into two figures. So that the majority charge carriers in the P region, if this is PNP transistor, the majority charge carriers are holes, and if we apply forward bias here, majority charge carriers will flow from emitter to the base. Similarly, here this junction is reverse biased. The minority carriers in N regions are obviously positive holes. So minority carriers are forward biased here, not majority carriers. No current is flowing for the majority carriers, but we get a little bit of current for minority carriers. And obviously, if we form the transistor, there will be a depletion region. One depletion region is in between emitter and base. One depletion region is in between base and collector. As emitter base junction is forward biased, the dimension of the depletion layer is very thin. But the collector base junction is reverse biased. That's why the width of the depletion region is very, very large here. If we keep on increasing the reverse bias voltage, the width of the depletion region is also increasing. So minority carriers flow in the reverse biased junction and majority carriers flow through the forward biased junction. So this is the transistor normal operation. If we add this above two separate pictures into one diagram, we can get this picture. That emitter base junction is forward biased, the depletion layer width is narrow, and here this is very, very large. And the current is flowing, that is IC, IE and IB. This is positive ions, as all of you know the basic function of PN junction diode when we apply forward bias and reverse bias. This looks like same. So moving to the next slide. This is again showing the basic transistor operation, distinctly showing the current flow through the emitter, through the base and through the collector. So majority current flows through emitter to collector. A little amount of current is diverted through base. So IE equals to IC plus IB. IC is the majority carriers. Also IC equals to IC majority plus ICO minority. That is, this is reverse biased as shown in the previous slide, that minority carriers are forward biased and minority current can flow through this loop. That's why IC is the summation of IC majority and ICO minority. This ICO minority is called the leakage current. Now this is the basic transistor operation. Look at this one circuit, that this is the base emitter at left hand side and collector emitter at the right hand side. The amount of current flow in the base emitter circuit controls the amount of current flow in the collector circuit. So actually base current is controlling the emitter current and collector current. That's why this BJT is called current controlled device. Remember, BJT is called current control device as base current is responsible for the current flow through the collector circuit. So this is showing the direction of current flow separately, IE, IC and IB. This is for NPN transistor. This is for PNP transistor. Now we know we should know what are the gains in the transistor. So as previously discussed, base emitter current changes yields large changes in collector emitter current. The factor of this change is called beta. So beta equals to IC by IB, that is DC current gain of transistor. Now beta is equivalent to hybrid parameters HFE on transistor datasheet. Now HFE equals to beta DC. Now one more term is there, alpha. Alpha is the ratio of collector current to the emitter current IE. less used parameter than beta in transistor circuit. Beta is mostly used. So alpha DC equals to IC by IE. The relationship between alpha and beta is alpha equals to beta by 1 plus beta and beta equals to alpha by 1 minus alpha. So IC equals to beta IB and again IE equals to beta plus 1 IB if we put the value of IC in the formula at IE equals to IB plus IC. So these are the modes of operation. When emitter based junction is forward bias and collector based junction is reverse bias, this is the normal active mode. The transistor operates in active region. But when both the junctions are reverse bias, this is in cutoff mode. Both the junctions are in forward bias, this is in saturation mode. Emitter based junction reverse bias, but collector based junction is forward bias, then this is in inverted mode. So this is again mentioned in this slide. So active mode, we can see that as in that base current opens a gate for a limited amount of current through the collector. If this limit for the collector current is greater than 0 but less than the maximum allowed by the power supply and load circuit, the transistor will throttle the collector current into a mode somewhere between cutoff and saturation. This mode of operation is called the active mode. So this is these are the general formulas. IC equals to alpha IE plus ICBO. And then ICBO is responsible for minority current flow. So alpha DC is nothing but IC minus ICBO. From this equation we are getting IC minus ICBO by IE. Now IC equals to alpha IE. So alpha equals to IC by IE. General value of alpha is around 0.99. But the general value of beta can be 500, 900, whatever. So we know IE equals to IC plus IB. Now IC equals to alpha IE. IE in place of IE we put here IC plus IB plus ICBO. Now if we solve the equation, we are getting that IC equals to alpha by 1 minus alpha into IB plus ICBO by 1 minus alpha. So IC equals to alpha by 1 minus alpha is nothing but beta. So IC equals to beta IB plus 1 plus ICU. Actually, values of alpha and beta vary from transistor to transistor. It is not fixed. Both alpha and beta sensitive to temperature changes. Beta generally called common emitter DC current gain. Here we can see some numerical problem. So if we go through the first problem, the collector leakage current is given 300 microampere for common emitter configuration. Beta given, we have to find leakage current for common base configuration. So leakage current ICU 300 microampere, beta given, we have to find out alpha. Alpha is coming 0.992. Now ICEO we know equals to ICBO by 1 minus alpha. It is shown in the last slide, that is ICEO equals to ICBO by 1 minus alpha. Now put all these and we will get the value of ICBO, that is 2.4 microampere. So what we can see? That leakage current is C configuration like ICEO is much more than the CB configuration ICBO. to the next problem. Here is another example. We can see that for a certain transistor, IB given, IC given, beta given, calculate ICB. So we know IC equals to beta IB plus ICEO. Now put all the values here. ICEO we are getting 0.4 milliampere. Now alpha equals to beta by 1 plus beta. We know. Put the values here. We are getting alpha. So ICBO equals to 1 minus alpha into ICEO. So put the values 1 minus 0.988 into 0.4. That is coming. ICBO is 0.0048 milliampere. So there is another problem, that is IB given, IE given, beta given. So IC equals to alpha E, IC equals to beta E. These two formulas we know. Now just put these values, we will get that if we apply this formula, then also 29.93 milliampere we are getting. If we apply this formula, then also 29.93 milliampere we are getting. This proves that we can use any one of these formula. So these are the suggested books for the students. If there is any question, please feel free to mail me at shunika.roy@gnit.ac.in. Thank you very much.